let's advance to where we left off. So remember I told you to don't forget about these two important tips for working problems. And I even used the word Hess's law. And honestly, we're going to get to Hess's law today. So Hess's law, these, you got it, right? So one of the things, I was looking at my notes and I didn't emphasize, it was in your notes on Monday, was this delta H, of course, is the change in enthalpy. And we usually say, reactions can be endothermic or exothermic. Of course, if they're exothermic, the delta H is going to be negative. If they're endothermic, the delta H is going to be positive. But the change in enthalpy of a reaction we usually call the heat of a reaction was going to be my point here. And then we said, let's just say that you have a reaction, but you don't have the reaction you want. And again, Hess's law. If the reaction you want actually is just a multiple of the reaction you have, you can multiply through by a factor of 2 or a half, and that's fine. You just need to adjust your heat of reaction at the end there by doing the same thing. We also said you can swing the reaction around the reaction arrow, and in that case, if it was exothermic, now it's endothermic. If it was endothermic, now it's exothermic. It's the same magnitude of energy associated. It's just now you reverse the sign. So, oops, skip aside. So in the last unit, we talked about balancing. We talked about chemical reactions being represented by equations. And we said if you balance the equation, then you have what we call the stoichiometry of the reaction. You have the mole ratio, okay? So honestly, though, if you have the heat of a reaction represented for a particularly balanced equation, you also have stoichiometry associated with that energy. I'll kind of show you what I mean. Okay, so for instance, say we have this reaction between iron and chlorine. Okay, it's an exothermic reaction, right? Negative heat of reaction. And let's just say that you're given this question. And in your homework, you're going to see what I would suggest you do, if you're into kind of doodling, is it says how much energy is released. So I would put delta H is equal to question mark. How much energy is released when 2.35 grams of iron is reacted. 2.35 grams of iron is reacted. Again, I just kind of like writing under there because it kind of hits me over the head with regard to what we know and what we're after. So in this case, and you're going to see it here in a minute, but know that this energy is the energy that's released from 2 moles of iron. 2 moles of iron. Why 2? Because 2 is the stoichiometric coefficient from the Fe. Okay, so that energy is associated with a specific balanced equation. Okay, so we can come up with these ratios. Okay, energy ratios, if you want to call them, like energy to mole ratios. And all that is, it's the same amount of energy. Now, we talked about this convention before, because you need to be careful about endothermic and exothermic and the signs. I guess more to the point, you need to be careful about the signs. Of course, the heat of this reaction is negative. It's exothermic. But if you go ahead and associate the word released with your answer, then you can put negative, but it's kind of redundant, okay? So in any case, can you see where 799 kilojoules of energy are released for every 2 mole of Fe, or 3 mole of Cl2, or 2 mole of the product formed, okay? So of course, to work this problem, we're going to use that relationship. So it's all about factor label. So to work this, actually, we're going to have to take that mass and convert it to moles, okay, using the periodic table. So the decimal number for iron is 55.85. So the mass of iron times the molar mass of iron will get us to moles, the cooked version of the molar mass of iron. Then we're ready to go ahead and insert that ratio you saw on the previous slide. That's 799 kilojoules of energy released for every 2 moles of Fe. Now, I'm going to go ahead and finish this the way it is, but honestly, if I were working this problem, I probably would put a negative sign right there. Why? Because it was energy released. But you're going to see we're just going to keep with convention by at least using the words energy released, and it's okay. So multiplying this out and keeping 3 significant figures, because that's what we're allowed in both the 799 energy term and the 2.35 mass term. So that's the answer. So we would have to say 16.8 kilojoules of energy are released when we combined that amount of iron with least sufficient amount of CO2. Okay, any questions about that? Yeah, I would. I really would. Kind of what you're saying. I would just keep this negative and keep my negative there. Yeah. One of these days I probably need to go through and clean up my slides, but I would prefer that. In fact, the 4 homework problems you're going to do, that's what I would do. Okay. Okay. Now I kind of got sidetracked, so I didn't diagram all of these 4 problems. And remember, though, that you have an extra couple of days, so these will be due Monday. So take a look at these. Of course, 13, 15, and 17, you have access to the answers to. Notice that, bless you. Honestly, I guess related to the fact that we're taking Chapter 6 out of order. Chapter 6 talks about gas laws and such. I need to give you a few hints for 15. Okay, so 15, you need to see these hints. Okay, and 17, you need to see this hint. So with that in mind, let's take a look. I won't spend too much time looking at those. Part. Oh, that wasn't right. Yeah, that looks right, doesn't it? So all at a glance here, this is what you're facing with regard to 13. It's really similar to the iron one. Okay, notice that instead of iron, instead of a reactant, actually you're given the mass of a product, the calcium hydroxide. You're given the standard heat of reaction is exothermic again, negative 65.2 kilojoules of energy. And recognize, like I say here, that what that means is that for every 1 mole of calcium hydroxide, because the coefficient is 1 from the calcium hydroxide, you release 65.2 kilojoules of energy. So then actually the first step that you're faced with is really kind of step 2 here. Use that mass of the calcium hydroxide, the 283 kilojoules, or kilograms, excuse me. You're going to have to calculate the molar mass of calcium hydroxide. Make sure to show your work like you will do on a test. And go from that mass to moles. Okay, and then once you have those moles, you're ready to plug in that ratio of energy per 1 mole of calcium hydroxide. Again, I would go ahead and stick with the negative, and then you don't have to worry about energy released. So 14 looks like this. Notice that if you read 14 a few times, with regard to the reactant, the octane, the C8H18, you are given the volume. And let me go ahead and, I say 1 gallon, but let's go ahead and knock that up to, let's go ahead and, it says just generally per gallon, so let's go with 1.00 gallon. Okay. So basically, it gives you, it wants to know how much energy you're going to get for every gallon of that you combust. And it says per mole of combustion, you get 5.48 times 10 to the 3rd kilojoules of energy released. And that's per mole. So what you're first tasked with, actually I have this as step 1, is you got to take that volume and get ultimately, you'll get to grams from that volume. We know that you can use the densities given, okay? So use the density, and in fact they went ahead and gave you the English to metric conversion between gallons and liters here, because you'll need that to get to grams of the C8H18. Step number 2, then you wouldn't have to break out a separate step then. You could just tack on the molar mass of C8H18 to get the moles. And you could even go ahead and continue that thought and plug in the energy per mole to get to energy. Okay, you don't have to separate this into 3 separate problems. Okay. So that's just kind of my hints there. This one has actually that slide, the assignment slide, it said that you need 2 hints for this one, okay, for A and B, actually for B and C, I guess. Basically, it's a really similar approach. You're combusting C4H10, and you're given the amount of energy released per 1 mole of C4H10, okay? And A, B, and C just gives you the amount of C4H10 in different ways. So A gives it to you in grams. Go ahead and knock out the energy released. B gives it to you in liters, okay? And it's liters of gas, actually. And B, if you read it also, and we'll talk about this when we talk about Chapter 6, gases, it gives you the conditions of that gas, or standard temperature and pressure. And under standard temperature and pressure, like I say up there in green, a volume of 22.414 liters will contain 1 mole. So just so we're kind of, just to kind of clarify, you're going to take that volume and you're going to plug in 1 mole over 22.4 liters. Oops, next one. I don't ever want to confuse you more than help you here. Okay, so for B, okay, you're going to take that 28.4 liters of gas, and you're going to plug in, since it's at standard temperature and pressure, 1 mole over 22.414 liters. That number might sound familiar to some of you. Okay. And then honestly, if you want to finish the problem, you're ready then to go ahead and give the energy per mole, which is that negative 22,877 kilojoules per 1 mole of the C4 compound. Okay, so you're done. Sorry it's so ugly. And the last one, C, again, since it's a gas, and you'd have to use PV equals nRT to solve for the number of moles. So honestly, C, I'm just going to give you the moles. So 0.503 moles of C4H10 is what you're dealing with there. That'll be your first term over 1, and then you can go ahead and put this term to go all the way then to energy. And the last one, I really got sidetracked, okay? But you're burning methane, and there's a hint for this one for, I think it's B, okay? Is that what it said? Oh, I didn't have it there. Good. Okay. So I'm just going to kind of leave you to it. It's similar to the previous one we looked at. Okay. This might, I'm looking, and it's been a while since I've done this problem, but I'm looking down here at C, and sometimes you've heard me give the advice, if you get stuck on a problem, okay, don't just stop. Okay. If you're like, say 100% efficiency, what the heck are you talking about? Just move on. It doesn't exist. Okay? All right. Can't do that with everything, but. So, I inserted this slide. So honestly, if you want to put a return to here, you can. Because related to kind of the pace of the labs, picking up here, this is the way I want to do it. Okay? So we're going to have a little bit of part 4 to come back to. In the meantime, I want to go on to the ever-famous Hess's Law, and then I'm going to go on to actually part 6 from there, and then come back and finish part 4. Okay, so this is where you need to be. I think it's funny. The possessive of anything that ends in S is kind of funny, so that's Hess's Law. Yeah. So Hess's Law, you're going to see we talk about kind of a big equation, an equation of interest, and little equations, okay? So what this is talking about is if a chemical reaction, and I'll go like this, if a big chemical reaction, big hairy chemical reaction, can be described in a series of little chemical reactions, okay? And if you know the heats of reaction of those little ones, if those little ones, I should say, if those little ones add up to the big one, And you know the heats of reaction for the little ones? You just add up the heats of reaction to the little ones, and voila, you have the heat of the reaction for the big one. Sometimes I call the big one the overall reaction of interest. And sometimes I call the little reactions for which you know the delta H's, I call those kind of puzzle pieces. So it's an addition sort of thing. So here in a minute, we're going to have to kind of add equations. So I'll kind of show you how that works. Okay, so if a chemical reaction can be described as adding little ones together, then the heat of the reaction for that big one, or reaction of interest, will be equal to adding the heats of reactions of the smaller ones. So we talked about, when we talked about enthalpy, we said it's a state function, or change in enthalpy, I guess I should say. State functions are independent of path. So this is to say, when we talk about those little reactions, it's not to say that this little reaction all happens, then this little reaction all happens, then this little reaction all happens. It's not that it happens all in that order. It's just that combined, they equal the overall reaction of interest. All right, so let's look at the combustion of benzene, C6H6. It's a ring sort of thing with alternating single and double bonds. Okay, so that is our big reaction. That's our reaction of interest, and sometimes the way I think of it is I'll put a little question mark delta H over here. So question mark delta H. Okay, we don't know the enthalpy change for that reaction. But somebody told you this is a Hess's law problem, and they said, yeah, that's fine. These are your three equations for which you do know the enthalpies of reaction. Okay? So we have the big one, the combustion of benzene. And then we have those three little ones. Those are what I call the puzzle pieces. So basically, we are going to, well, how do I say this? We are going to use these equations of interest to ultimately come up with this delta H question mark. But here's the deal. We can't use them straight out of the box. Okay? We're going to have to do some manipulating with those puzzle pieces. Turning them, reversing them around the reaction arrow, scaling them up. Okay? So before I talk about, let me see, yeah. Before I kind of dive into the problem of applying Hess's law to the combustion of benzene, I want to explain why, when they said carbon as graphite, why that's such a big hairy deal. There are at least 3 forms of carbon. They're called allotropes. Carbon is a solid, right? Okay. And you're familiar with, for instance, 2 allotropes. You know, for those of you gals wearing diamonds, okay, that's one allotrope of carbon. For those of you using a graphite pencil, that's another allotrope form of carbon. Okay, they differ by the conditions at which they've been dwelling over the last, hundreds of thousands of years. Okay, so the benzene problem, okay, it said actually, didn't it say carbon as graphite, I think, solid carbon as graphite, and it makes a difference. The energy, the enthalpy associated with carbon in these different forms is different. So we have, these are how the carbon atoms are arranged in graphite, how they're arranged in diamond, how they're arranged in something called a buckyball. So I don't have a whole lot to add. I just want to emphasize, and we'll be talking about solid states in, I think it's Chem 2, just in general. So there's what your lead pencils do. Isn't that funny how lead pencils have nothing to do with lead? They're graphite, they're carbon. Yeah. Okay. And then this is buckyballs. Okay. So back to our problem. So the way you work this, and I'm not saying you have to work it this way, but a few hints is, my first hint is to organize your problem, kind of get your bearings. Clearly describe your puzzle pieces and number them. 1, 2, 3, 4, 5, however many puzzle pieces you have. The equation of interest doesn't get a number. Okay, it's question mark delta H. And then what you do is somebody told you you're going to be using those puzzle pieces to your advantage. So you look at each puzzle piece and you compare it to the overall reaction of interest, the big reaction. And you see what you need to do to use it. Sometimes they're more obvious than others. But can you see where this one, a good place to start is you can see that we have that in common. Does that make sense? Yeah. So one of the things right off the bat is this puzzle piece is backwards. Does that make sense? So the way I'm actually going to manipulate this first puzzle piece is to reverse it. Now, in my answer keys, what you'll see is when I manipulate a puzzle piece, I call it prime, kind of this little prime over here. It's not puzzle piece number 1, it's puzzle piece number 1 prime. And then we said last lecture that if you reverse it, the enthalpy of the reaction is the same magnitude but opposite in sign. And so instead of requiring 49.0 kilojoules of energy, now this will release 49.0 kilojoules of energy. Okay, does that make sense? So don't forget about the primes. Okay, and we ended up reversing, since we reversed it, we changed the sign. So we set that one aside. Sometimes, I'll say students, because I don't think I get into a hurry these days to do these sort of problems. Sometimes students get into a hurry and they don't want to rewrite the prime, the manipulated one. Okay, and I think that's where things start to fall apart. So here was our second puzzle piece. And if we look at, see there's no carbon, there's no oxygen. You're like, dude, how can we use this? Well, of course, the CO2. And it's on the right side, right? So the reaction of interest has 6 CO2s, but our puzzle piece has 1 CO2. So we can scale that up, okay? But if we scale it up, notice then that's going to have to scale up all of the, the 2 reactants too. So we'll have 6 carbons, 6 O2s, and 6 CO2s. Why? Because our reaction of interest has 6 CO2s. Then, of course, if we do that, we're going to keep the same sign for our heat of reaction, but we're going to take that negative 393.5 times 6. And that gives you negative 2,361.0. Okay, does that make sense? It's funny because I get excited when I get to the end of a Hess's Law problem because it's kind of like a Hail Mary. We're going to do the same thing to the third puzzle piece, and we're going to hope we manipulated them right. We're going to add up our 3 primes and hope we get the equation of interest. That's how it works. And usually we do. Okay, so we set that one aside, turn our attention to the third one. And so the third one, notice that we have O2, okay, but I wouldn't focus on the O2 because I think we have O2 in one of the other puzzle pieces. I would focus on the H2O here. Of course, it's on the product side, okay, in the reaction of interest, but there are 3 waters on the product side in the reaction of interest. So we're going to multiply everything by 3. That includes the stoichiometric coefficients of that puzzle piece, and then it also includes the heat of the reaction. So now, according to one of the first slides of this part, if 1 prime plus 2 prime plus 3 prime, if those manipulated equations do give us that pink equation, then we can add the heat of reaction 1 prime plus 2 prime plus 3 prime and get the heat of reaction of interest. So one of the things, and I'm not really thrilled on how this slide builds this. If I were going to go ahead, these are our primes, and so I really would suggest you do this addition. If I was going to do it on an answer key, I would actually take my reaction arrows and line them up. And then, honestly, all we're going to do, you can do this a couple different ways. You're going to see me kind of reduce it as I go. You are going to take your reactants, and you're going to add them together. and you were going to take your products and you were going to add them together and put them right there. Okay? That's basically what you're going to do. So what my builds do is it's okay. They basically kind of simplify things as I go. So again, I would rather that the reaction arrows be lined up. But can you see where if you have the same thing on both sides of the reaction arrows, like those 6 carbons, they can go away. We don't got to bring them down. Okay. Similarly, we have 3 hydrogens on either side. They can go away. If we did bring them down, there would be no foul. There would be no harm, no foul. Basically, you would end up with 3 hydrogens and 3 hydrogens, and when you simplify your summed reaction, they would go away. So here's a deal where we have oxygens on the reactant side. We have 6 moles and 3/2 moles. And if you're like me, I have to concentrate on basically, if you take the 6 halves, or 6, and turn them into halves, you got what, 12 halves? So you got 12 halves plus 3 halves, and this is easy to make a mistake. Okay, so you end up with 15 halves oxygen. So here's our 15 halves oxygen. The only other thing that's on the reactant side is the C6H6. On the product side, we have your 6O2 and your 3H2O. And you should be all smiles, because like, hey, that was the reaction in the pink box. Okay? It's not an accident. It's like somebody gave you that stuff. All right. So since we did indeed with our 1' plus our 2' plus our 3' get the reaction of interest, okay, then we can go ahead and sum their enthalpies of reaction for those prime reactions. Staying organized is a good thing. Okay, so just reminding you what they are. Okay, reminding you what these were. And always remember that, for instance, the first one we reversed, the second one we multiplied by 6, the next one we multiplied by 3. You know what? Sometimes you have to reverse and multiply it by something. Sometimes you have to multiply it by a fraction to get it be useful in your reaction. Now you need to be really careful. It's easy to lose a negative sign and then you don't get the right answer. But if you go ahead and sum those 3 exothermic heats of reactions, you'll end up with a whopping negative 3,135.4 kilojoules. So remember when I said about how to round stuff? And I said we don't do much addition and subtraction. Well, we're doing addition and subtraction here. So here we need to round according to decimals. And this actually, that's important because some of you might be saying, huh, Mrs. Snipes? There's only 3 sig figs there. But I would be saying, since you are summing these, you round according to decimals. And there is 1 decimal for each of these terms. So that's why you're allowed 1 decimal. So that's Hess's law. Not too bad. They are fun. So let's take a look at all the fun you can have. Now these I did not get to at all. And if I remember right from last fall, some of these are harder than others. Makes sense. Where is it? There it is. Okay, so take your time. Notice they aren't numbered 1 and 2. But if you read it, what you'll see is this is my reaction of interest. Okay, so I'm after the enthalpy change here, and these are my reactions that I can manipulate. Okay, they're so fun, I think I will just let you go at them. The next one, okay, it's similar pattern. Looks like we have reaction of interest in the top. Oops. Really? And then 3 puzzle pieces. Okay, reaction of interest. 1, 2, 3. Do not, and you probably will, I know, they say not to set your outside. Do not simply try to manipulate them as they're written for you and then try to do some sort of wild-ass sort of adding. You might get the right answer, you might not. Bottom line, if you don't rewrite them, and they just are terrible. They're terrible for you and terrible for me. So that's all I got to say. 2 more. That was 69. Oop. 3 of 4. Huh. Well, where'd you go? Did I really get that sidetracked? Okay. There's this one. Okay. Where again, reaction of interest, and looks like 2 puzzle pieces. Okay. Some of them, like I said, are trickier than others. And the last one, I don't think there's any snags. It's this one. It kind of gives it away, doesn't it, where just kind of glancing at it, you know, we have these enthalpies of reaction, and we don't have that one. Okay, Hess's law. Cool. Well, double check. Yeah. I want to keep the standard molar enthalpies of formation. I love that standard molar enthalpies of formation. I want to hold that back, take a running start at that on Monday. So that's it. Okay? So these will also be due Monday.
Since we're not class Friday, will you be here at all?
No, I won't. But you got my phone number. I do take texts. And I will be able to, we're going to be in the sticks of Mississippi